yet. Have you guys heard of a choppelganger? Not a doppelganger, but a choppelganger. Anybody heard of it? If something's chopped, it's not great, right? Chopped. It means bad, right? Okay, you guys know what a doppelganger is? So how I've seen this used is it's like the Temu version of a doppelganger. So you kind of look like them, but not as good as that person. A choppelganger, which I kind of get a kick out of. Yeah, we'll see. All right, so coming back to this, we'll see if that one shows up or not. But here we go. I agree with you that with 5, it takes 3. Now, is there anybody in here who doesn't really understand what we've done to get these numbers? Riley and Jonah, you guys cool with this? Do you want to see where these 3 come from? Okay, so if we have a regular or any 5-gon, so for example, this is a pentagon, right? If I want to make this shape, I can draw one diagonal right here and another one right here. And do you agree that with these 3 triangles, I've made this entire shape? Like that's all we're doing, and it only takes 3. If I make a 6-gon or a hexagon instead, it will take 4 of them. And we could do the same thing. You can draw it to confirm if you'd like. But what we see is that the number of sides is always 2 more than the number of triangles. So if I have n sides on some figure, it would just simply be n minus 2 right here. Now, where we're going to use all of this good stuff, and where we're going to use all this is kind of like a preface to 4.1, and it's not chapter 4, it's actually chapter 6, 6.1, where we are going to be talking about polygons this chapter. And then 6.1, did we already name it? Okay, so the polygon angle sum theorems. Now, Sophia, you're going to find and you're going to see that there's a lot of things that I write shorthand that whenever you don't know what I've written, please call me out, like right away. Like, I don't know what, like these ones, nothing too crazy, but they're shorthand for like all of this stuff, okay? Okay, so we are going to be looking at some polygon angle sum theorems. And we're going to use the idea that we worked out with this little table right off the bat to make sense of these things. So without any further ado, we're just going to start right in and see if we can't work a theorem out of this. So right from the get-go, we get our first theorem of the chapter. I suppose we should probably define a polygon first. A polygon. Now, how many of you think you are comfortable and you could tell me if I draw something, if it's a polygon or not? Okay, so at least one of you can. What do you think of when I say polygon? So it could have 5, that'd be a pentagon. Are there 4-sided polygons? Yeah, they're squares, they're rectangles, they're trapezoids. Are there 3-sided polygons? Triangles is what they're called. Are there 2-sided polygons? No, so I'm going to sketch a couple up here. I'm going to do it in like this purple violet color here. I just want you to tell me, you don't have to draw these, just is this a polygon? That's not a polygon. Why? Because why? They don't connect nicely, right? Like I have all this extra stuff. What about this one? Now it is. So there's a difference here. One, these don't cross over anymore, so that's okay with it. But the other part, if I take just that one out, is it a polygon now? No. So I think that we have to require that if it's going to be a polygon, we'll say it is a closed figure with sides that don't cross. And we could probably be more specific with this if you guys need me to, but I think that this is as concise as I can be. It is a closed figure, and we can think of it almost like just a shape that we might draw. Any shape where the sides don't cross each other. That's it. Okay, so with polygons, you guys know a few of them right off the bat. There's a really lazy way to name them. And I think we might have talked about this last class. There's really formal Greek route that we can go. So for example, a 3-sided polygon is a triangle, is a real name. How about a 4-sided polygon? It could be a square, it could be a rectangle, it could be a trapezoid, but it's a quadrilateral. What about a 5-sided? Penta. What about 6? Hexa. And these I don't expect you to know, just so you know, but you've probably heard most of them. What about 7? Hepta with a H-E-P-T-A, heptagon. About 8? Octagon. 9? It's a nonagon. 10? Decagon, like deca as in decade. 11? Hendeca is what that one is. Now, here's the cool thing. You don't have to memorize or speak Greek to get these. Check it out. If I have a 7-sided polygon, I'm not going to call it a heptagon. I'm going to call it a 7gon. That's it. We're just going to use that number. So we have an easy way to name these. Follow-up kind of definition with these. And this is weird because we don't usually have follow-up definitions. If I say we have a regular polygon, these are very specific. I'm going to give you a regular quadrilateral. It's called a square. What makes a square compared to a trapezoid or a rectangle? 4 equal sides. And what about all the angles on the inside? 4 right angles. So we have all the sides are congruent and all the interior angles are congruent. So we're just going to say, hey, if it's regular, we'll just say all sides and interior angles congruent. Okay. We have this nice definition of what it means to be a polygon. And there's some other little pieces. Have you guys, and I don't want to have to write all these down because it's just going to turn into pure vocab, but if we talk about convex versus concave, does that ring a bell to you guys? What's the difference? If something is like this polygon right here, which 1, 2, 3, 4, 5, it's a really weird 5gon. Is this convex or concave? Why? It's like it's caved in here. Now, if we wanted to be really formal with it, we would say that if you extend any of the sides, they don't run to the inside of the figure. If I extended this, would it cross through the interior of it? That yellow one would, right? It crossed inside. That means it's concave. It's a real thing. Just caved in is the easier way to think about it. Okay, concave versus convex is the other part that I'm not going to write, but it's worth making sure that we have them at least ready to think about. Okay, so with these polygons, we're going to jump right in, where we're going to try to find, and not just try to find, we're going to define for ourselves our nice first theorem. So right off the bat, here we go. Theorem 6.1, and we're going to say it's the polygon, an INT. Do you need me to write larger also? Yep, I got you. And then the other thing tomorrow, I'll clean off this. If you have to scoot forward, or if you just want to scoot your desk forward, you also can. I will try to write bigger though. Okay, so let me try to write bigger now. Theorem, THM 6.1, the polygon interior, which I'm just going to shorthand INT. And what is this symbol again? Angle. And this last symbol, sum. So I'll just write the word sum here. Okay. We just found that there's a way to calculate how many triangles it takes to make a bigger figure. What do we know that all the interior angles of any triangle always add up to? So of triangles, 180 every time, right? So if we're looking at these, if I know that any n-gon can be made by n minus 2 triangles, and we know how many sides n something has, we can just plug it directly into that. So here we go. Given, and we're going to write our theorem, given a convex, which just means it does not cave in on itself, n-gon, the interior angles will sum, which what's another word for sum? Add up to, and I'm going to let everybody catch up. I'm going to go grab my drink. Ooh, maybe. Yep, it's back there. If I have an n-gon, how many triangles did it take? N minus 2 of them, and each of those n minus 2 triangles has how many degrees? 180. So check it out. It's super straightforward. N minus 2 times 180 degrees every single time. Now, there is a corollary for this that I want us to kind of try to work out, but I want you guys to work it out rather than me just saying, here it is. Cool. Before we move on, any questions about this theorem on its own? Okay, so let's just jump right in with an example, and then we'll work out the corollary. So there's my whole theorem. This is what it will always sum to. What is n? The number of sides. Awesome. So for our example, all I want us to do, and we'll do a couple of this, we'll use this theorem, and we'll probably extend it a little bit for at least this next one. I'll keep the theorem up. On A, I want us to find the sum, and I'm just going to say the sum of interior angles of, THM is my shorthand for theorem. Find the sum of the interior angles of a, let's say it's an 11 gon. A hendecagon is what we're after here. Now, I don't know why you would need to do this for an 11 gon in particular, but the next little follow-up, we'll see some nice places where it might make sense to do. How do we even begin this problem? How many sides does an 11 gon have? 11 of them. How many triangles will it take to make an 11 gon? 9 of them. And each of those triangles has how many degrees? 180. So check it out. If n is 11 in this case, and we just use this theorem where we get this lovely n minus 2 times 180, and we know that for an 11 gon, the number of sides is 11, I think we have a pretty straightforward way to solve this. I think. What's 11 minus 2? So we'll just say this implies to ourselves that this is 9 times each of those triangles one more time has how many degrees? 180. Perfect. And now it's just a matter of doing 9 times 180. And we can save ourselves a ton of time with it. So if you want to come grab a calculator here, you can. If you want to practice a little bit of long multiplication or grab one of the back ones, they are not coming back to the classroom consistently, so these ones might be the better ones to go with. Sevilla's about to pull one out of her backpack because it didn't come back to the classroom, which that's fine. What's 9 times 180? 1620, I think. But somebody should verify that. Are there a bunch of calculators here still? Okay. I think it's 1620. I think it's 1620 because 9 times 100 plus 9 times 80. Okay, 1,620 degrees is what I think it is. Looking at this, again, if we're out of those ones, there are these ones also that I'll hook it up with. Okay, well, here's a calculator just in case. Cool. Okay, super difficult to do. Should we do another one like this, or do you want to try to figure out the more fun part of it? Okay, so I'm going to give you guys a couple minutes with one another, and we'll just see what we can come up with. So we're still going to use this theorem. Before I just give you the problem, questions about any part of this? Bet. Okay, so check it out. We're going to switch the way this problem is presented a little bit. I'm going to tell you instead on this problem, a regular polygon, which, what does regular mean again? All the sides and angles are congruent. So a regular polygon has an interior angle of, and let's see how big we want this to be, of, lost my spot here, sorry. I had an ugly one a second ago. Where did it go? Here we go. 172.8. 172.8 degrees. So it's a regular polygon, and each of the interior angles on this polygon is 172.8 degrees. What I want you to do for me is answer, how many sides? Okay, for this, it is not a super obvious question, but we have all the tools necessary. I want you to try it first. If we have to ultimately talk about it as a class, I'm good with it. But I want you guys to play around with this, be okay with being wrong. I want to see what you come up with first. Sweet. Do it to it. I want to hear you talking. All right, our algebra muscles are a little bit rusty. That's okay. Check it out. Let's jump in and let's see if we can't do this. Up on the board, we have n minus 2 times 180. And that's all divided by n equals 172.8. Okay, who in here loves division and having fractions? Fair. What are we dividing by? What undoes the divide by n? Let's multiply by n. Which side? Both of them. So let's do that right off the bat. I'm going to switch colors because that one's kind of hard to see. If I multiply this side by n and this side by n, on the left side, they divide out. Now, I'm going to go one step further. I have n minus 2 times 180. What is this just asking to be done? I'm just going to do it in this step. Let's distribute. What's 180 times n? 180n minus what's 180 times 2? 360. And that is all equal to, I think, 172.8n. At this point, I have everything set up so that we can move n freely around to both sides, right? We just need to isolate it. Do you want me to subtract 172.8n and then add 360? Or do you want me to just subtract 180n? Okay, so I'm going to do 2 steps in one here, and I'll switch so I can see it. We'll subtract 172.8n. And if you subtracted the 180, you're fine as well. I'm going to add 360 to both sides. It doesn't matter. This is just going to give us a positive value here. And that's 172.8, right? Okay, so that looks like what, 7.2n? 7.2n must be equal to 360. We are one step away. If I wanted to finally get this to solve for n, the number of sides, what's the last little thing we have to do? Divide by 7.2. And I think that this winds up being 50. What we have just found is if you wanted to make a 50-sided table, which would be obnoxiously large, but if you wanted a 50-sided table, when you're going to cut your piece of wood, each of those interior angles would have to be 172.8 degrees. Now, nobody's ever going to build a 50-sided table. That's kind of obnoxious. But if you wanted to build a table that's more than just 4 sides, which I think makes sense because a lot of families have more than 4 people, if I wanted to have a table with 8 spots or 7 spots, we could figure out exactly what is the angle that we need to cut this at, so we have 7 equal spots to sit at. And if you want to have a nice business meeting and there's 7 people, or 11, or however many you might want to make, we now have a way to get that angle exactly as we need it. Okay, should we do one more similar to this? Let's make an easier one with less ugly numbers, because this problem, same techniques and everything, a little bit harder though. Okay, so we'll have one more that I want you guys to knock out. Each angle of regular n-gon is, let's make this one much nicer, 108 degrees. I want to know the same question, how many sides? So instead of that 172 point awful number, it's 108. I want to see if we can replicate this. N-gon. Or which are you looking here? Yeah. N equals 50. Or, and this one just says n-gon. And I'm going to clear, do you mind if you sit up here? I'll keep trying to write bigger, but it's going to be a challenge. Or if you just want to move forward. But if you do want to sit here, it's a comfy seat. So that's something awesome. It's up to you. And do we need a brain break also? Okay, I saw somebody said no. That's pretty awesome. Sonny doesn't want a brain break. I get it. I'm sorry. Way too many. Way too many. So let's look. Is this the one right here? So 108n. So you get 108n minus 360. So you're close. You don't subtract. How do you get this? You're so close. If 72 times n is 360, how do you make it say just n? You don't subtract 72. What do you do? Good. I think that's the only air pocket thing that I have. No, I got other ideas. So honestly, I would just subtract the 180, and then you get negative 72. Like, it's potato there. How's it going? So let's check it out. In this one, we get the same thing. It's going to be our n minus 2 times 180 over n, but instead of being this, it's the exact same thing. But yep, the only thing that changes is what this interior angle is.
Oh, which is
108 instead. Yep. Don't forget to divide by n on the left side. Yep. So kind of both, because here you divided by n and then you multiplied. So because we have to say cut that, and like this is all the angles together, and we're trying to cut it into n equal pieces. Yep, perfect. Now you'll multiply. Perfect. All right. So coming back together, I know some of you guys are still working. We should confirm here that all of this is about the same. Now, I think if I take one step forward in the problem, we could have 108n equals n minus 2, n minus 2 times 180. And all I've done is I took that divide by n step and I just went one step further with it. Do you all have this on your page? Okay, once we're here, there's some pretty handy stuff that happens. This is always going to be n minus 2 times 180 every time that we do this, which means every time we could just jump right to calling this 180n minus 360. And it's going to be the same as before. So let's just kick forward 1. I'll distribute here and get this is 180n minus 360. Now I'm going to do one thing different on this problem. Last time we made it so that it was positive, but it doesn't really matter with the algebra as long as we divide by the right thing. If I just subtract 180n from each side, I wind up with a negative here, but it's not the end of the world because I also have a negative on the other side. When I get to this point, there's only one step left. That wasn't a question, but it can be. I don't need to subtract anything even. Let's just divide both sides of this by negative 72. And we've now found that this was a how many sided polygon? 5. We just had a pentagon is what we were working with. Now, what this corollary, and that's just a follow-up to a theorem that we've just worked out, is if you have a regular polygon, we have a way to calculate a single angle of that polygon. Like, it's super easy. Yes, sir. N would not be negative because then you would have a negative number of sides. Yep. Cool. All right. So from this, we're just going to get a quick follow-up or a corollary. And we'll just call this corollary 6.1. And remember, a corollary, just something that shows up after a theorem. It's not cool enough to be its own theorem, but it's an idea that we can use. corollary. Okay, corollary 6.1 simply says a regular n-gon, and regular meaning what again? All sides and angles are congruent. A regular n-gon will have each interior angle of measure, and then we're going to think about this again. If I want to know what each of them are, I just need to find out all the total angles together, add it up, and then divide it by however many there are. And how do we find the total sum of those angles? Something with n minus 2. So here's all the total angles added up. And then we just cut it into how many pieces? N of them. And here it is. And this is what the idea that we were just using on our example without ever stating it. We had this kind of sitting behind us, and we were able to work it out. Okay. So we have a way now to calculate all the interior angles or a singular interior angle of some polygon. If we talked about interior angles, have we ever talked about exterior angles? Yeah. Do we have any nice exterior angle ideas? So alternate exterior for sure, if we get parallel sides. We're going to do the same, or not the same thing, but something similar. Should we do a quick brain break? Okay, real quick, little part of this. We talked, so far today, we've talked, everything has been about the interior angles of something. So we're going to work out, instead of the interior angles, we're going to talk about exterior angles. Now, to make this easy, I think that we could just work with regular figures, and they don't have to be perfect, but let's talk about the exterior angles of a polygon. Now, just like we did with the interior, there's a nice way to think about this. Now, if we work with the nicest possible examples of these, they should be pretty obvious. And let's try our best. We'll just assume that they're all regular shapes. So check it out. If I have a nice triangle, can you tell me what each of these angles should be if it's a regular triangle? They should all be 60 degrees. And I'm just going to mark them as such. Now, for our exterior angles, as long as we're consistent in how we do it, I don't really care the order that we go. I'm going to use just this light blue line to extend out. If I extended this bottom side a little further, I would get an exterior angle right here. If I do it the same order, so I went left to right, and then I'll go left to right, I'll extend this one to get an exterior angle up here. And I'll do the same thing down here. So that on my three-gon, how many exterior angles did I just draw? I drew 1, 2, and 3. Okay, now this is with a perfect, nice triangle. And it doesn't really matter if it's nice and perfect, but it's going to make it easier to think about. For a four-gon, hypothetically, what's the nicest four-gon that I could draw? A square, or a rectangle would also be nice, but I actually am going to draw a rectangle since it's here. If that is a lovely four-gon and it's a rectangle, then all of those are right angles. Now, whether we knew they're right angles or not, I recognize that there are four angles and they have to add up to 360. It doesn't matter if they're really all four right angles or not, but this is a nice one to think about. How many exterior angles should I get on this? So one here, here, and I'll just mark them all again, 3 and 4. I want you to do the same thing one step further with a 5-gon. So we have a 3-gon, a 4-gon, and a 5-gon. And I would work as best you can with a regular 5-gon. I'm not going to tell you the angle of it, but if you look back at the work that we've done in class, maybe you'll have that angle written somewhere. It's about like that. Make it nicer. What I want you guys to do is for each of these, I want you to tell me what the exterior angles of each of these add up to every time. So 5 exterior angles here. You may have to do a little bit of work to figure out what these interior angles on the inside of this one each are, but you have the tools to do that. Cool. I'll give you a couple minutes. My guess is that this is probably where class is going to end, but we'll see if everybody does it super fast. Maybe it'll go a little bit further.